Today, we're going to talk about one of the most important pieces of equipment in industry, buildings, and water systems, the centrifugal pump. You might not see it every day, but the water coming out of your tap, the cooling in a skyscraper's air conditioning, and even the slurry moving through a mine, all of that is likely moved by a centrifugal pump. So here's the question: how many types of centrifugal pumps are there, and which one should you use when? In this video, I'll explain the 5 most common types in plain, simple language. First, let's quickly cover what a centrifugal pump actually does. Inside the pump, there's an impeller that spins at high speed. It throws the liquid outward by centrifugal force, and that motion creates pressure. Unlike a positive displacement pump, which works like squeezing toothpaste, a centrifugal pump is great for moving large volumes of liquid at low to medium pressure. The flow is smooth and easy to control. But no single pump works for every job. So let's go through the 5 types one by one. Type number 1, the end suction centrifugal pump. This is the most common type you'll see in industrial and commercial buildings. The name tells you how it works. Liquid enters axially from one end, the suction end, and then discharges at a 90-degree angle from the top. The design is simple and cost-effective. One of the best features is called back pullout. That means you can remove the rotating assembly, the impeller, shaft, bearings, and seal, without disconnecting the pipes. That saves a lot of downtime during repairs. End suction pumps are ideal for HVAC water circulation, light chemical transfer, agricultural irrigation, general water supply, and fire protection systems. They typically handle flow rates up to about 5,000 gallons per minute and heads up to around 500 feet. The main limitation is that they can't generate very high pressure. They're also not well suited for thick fluids or liquids with a lot of solids, because efficiency drops and wear becomes a problem. Now let's move to type number 2, the split case pump. This pump is also called a double suction pump in many cases. The casing splits horizontally along the shaft centerline. You can unbolt the top half and lift it away, exposing the impeller, wear rings, and bearings without touching the pipes. The key feature here is the double suction impeller. Liquid enters from both sides of the impeller at the same time. That balances the axial thrust on the shaft, which is a big mechanical advantage at high flow rates. Less thrust means longer bearing life and lower maintenance costs. Split case pumps are used in municipal water distribution, large fire suppression systems, big HVAC systems, power plant cooling circuits, and flood control. They can handle enormous flow rates, from 200 gallons per minute all the way up to over 100,000 gallons per minute. Heads go up to about 600 feet per stage. The downside is size and cost. These pumps are physically large and much more expensive than end suction pumps with the same flow capacity. They also need more floor space and careful alignment. Type number 3, the multistage centrifugal pump. When one impeller isn't enough to generate the pressure you need, you go multistage. These pumps have 2 or more impellers arranged in series inside a single casing. Each stage adds more head. A 4-stage pump develops about 4 times the pressure of a single-stage pump with the same impeller size. In a horizontal multistage pump, fluid enters the first impeller, then flows into a diffuser or crossover passage, then enters the second impeller, and so on until it exits at the final discharge. Some designs face all impellers the same direction, while others alternate directions to balance axial thrust. Vertical multistage pumps are often called booster pumps. They stack the stages vertically in a compact form, which is perfect for tight spaces like high-rise building water supply systems. For extremely high-pressure applications like boiler feed or reverse osmosis, you use barrel-type multistage pumps with a forged casing rated for over 1,000 bar. These pumps are used for boiler feed water in power plants, high-pressure water injection in oil and gas, reverse osmosis desalination, high-rise building boosting, and pipeline booster stations. They can achieve heads over 5,000 meters. That's over 16,000 feet. No other centrifugal pump type can do that. The trade-off is mechanical complexity. More stages mean more seals, more wear rings, longer shafts, and greater sensitivity to misalignment. Maintenance requires trained people and precision tools, and the first cost is significantly higher. Now let's talk about type number 4, the slurry centrifugal pump. Slurry pumps are a specialized category. They're engineered to handle fluids with suspended solid particles. If you try to run a standard centrifugal pump on slurry, it will fail quickly due to abrasive wear or clogging. A slurry pump has thick, replaceable liners, enlarged flow passages, and a rugged impeller. The most critical design decision is the material selection for the wetted end. High chrome white iron gives excellent abrasion resistance for sharp, fine to medium particles. Natural rubber or polyurethane liners are better for rounded particles and corrosive slurries. And for acidic or alkaline slurries, you might need duplex stainless steel or Hastelloy. The impellers are usually semi-open or recessed vortex designs with wide, thick vanes and generous clearances. This lets oversized particles pass without jamming. Hydraulic efficiency is lower than a clean water pump by design, but that's an acceptable trade-off for reliability and wear life. Slurry pumps are used in mineral processing for copper, gold, iron ore, and phosphate. They're used in coal washing plants, dredging operations, sand and gravel operations, power plants for fly ash and bottom ash handling, paper and pulp manufacturing, and tailings management. They can handle slurry densities from 1.1 to 1.6 specific gravity, and sometimes over 2.0. Particle sizes range from fine clay up to coarse gravel over 100 mm in some dredge pumps. The limitations are significant: lower hydraulic efficiency, higher energy consumption, and rapid wear of wetted parts, which means you need a planned replacement program for liners and impellers. Overdesign or underdesign for a given duty is a common cause of premature failure. Finally, type number 5, the submersible centrifugal pump. These pumps are designed to operate while fully or partially submerged in the fluid they're pumping. The motor and pump are hermetically sealed in a single unit and lowered into a sump, well, wet pit, or body of water. Because the pump is already immersed, it's always in a flooded suction condition. That means no priming is ever required, and cavitation risks are much lower compared to pumps that have to lift water from a lower level. Motor cooling is critical. In most designs, the surrounding fluid cools the motor. For clean water borehole pumps, that works directly. For sewage and slurry pumps handling warm or low conductivity fluids, an internal oil-filled or water jacket cooling system may be used. Shaft sealing is paramount because motor flooding is a catastrophic failure. Modern submersible pumps typically have two seals, a primary mechanical seal on the pump side, and a secondary seal on the motor side, with a barrier chamber between them. A moisture probe can alert operators before the motor fails. For sewage applications, submersible pumps often use vortex impellers, single-channel impellers, or semi-open chopper impellers that can pass fibrous solids and rags without clogging. These pumps are used in municipal wastewater collection, groundwater extraction and borehole pumping, construction site dewatering, stormwater management, aquaculture, mine dewatering, and residential deep well pumps. Performance ranges vary widely. Borehole pumps can handle 0.1 to over 500 cubic meters per hour with heads over 600 meters. Sewage pumps can go from 5 to over 20,000 cubic meters per hour with heads over 100 meters. The big advantage is that submersible pumps eliminate the priming problem entirely. Installation is simpler. You don't need a pump room. Noise levels are low because the motor is underwatered. The main challenge is maintenance access. You have to lift the pump out of the installation for any inspection or repair. In deep boreholes or large wet wells, that requires lifting equipment and careful planning. In smaller sizes, motor replacement after a winding failure is often cost prohibitive, making the whole unit disposable. So let's do a quick side-by-side comparison. End suction pumps are best for general industrial and HVAC service. They handle clean to mildly contaminated fluids, with medium head around 500 feet, and maintenance is easy with back pull-out design. Split case pumps excel at high flow water and fire suppression. They handle clean water, with medium-high head around 600 feet, and maintenance is excellent because of the split casing. Multistage pumps are for high-pressure processes and boiler feed. They handle clean to slightly corrosive fluids with very high head over 5,000 meters, but maintenance is complex and requires specialists. Slurry pumps are for mining, dredging, and ash handling. They handle abrasive and corrosive solids with medium head, but you need planned liner replacement. Submersible pumps are for dewatering, sewage, and boreholes. They handle everything from clean water to raw sewage, with varying head ranges, but you always need lifting equipment for maintenance. Now, how do you actually choose the right pump? Here are 5 key criteria. First, your hydraulic duty point. That means the flow rate and total head you need. You want to match the pump's best efficiency point to save energy and reduce mechanical stress. Second, fluid properties. Temperature, viscosity, vapor pressure, pH, specific gravity, and solids content all affect material selection, impeller type, and seal design. Third, net positive suction head available, or NPSH. This tells you whether the pump will cavitate. Submersible and vertical turbine pumps have naturally good NPSH characteristics. Fourth, system layout. How much floor space do you have? How deep is the installation? How easy is it to access for maintenance? Fifth, life cycle cost. Don't just look at the purchase price. Consider energy consumption, expected maintenance intervals, and parts availability. So to wrap up, centrifugal pumps are everywhere in our industrial, municipal, and commercial infrastructure. Understanding the differences between in-suction, split-case, multistage, slurry, and submersible designs is the foundation of good pump selection. The wrong pump for your application will fail early, waste energy, and cause unplanned downtime. The right pump, properly sized and specified, can give you decades of reliable service. For any complex or high-stakes application, always consult a qualified rotating equipment engineer or work directly with a pump manufacturer's application engineering team. Review the pump datasheets, performance curves, and dimensional drawings against your actual system hydraulic model before you issue a final specification. Thanks for watching. I hope this clears up the different types of centrifugal pumps and helps you make a better choice for your next project.